Good day and welcome back to part 2 of our discussion on implicit differentiation. In this video we are going to investigate a very common example. And that common example is we are given some implicitly defined curve. You know, this was our motivation in the previous video. Graphically that's representing the equation of a circle with radius 1 centered at the origin. And what we'd like to do is find dy dx and then answer a couple questions based upon that dy dx. So our general rule of thumb when it comes to implicit differentiation is we take our equation, we differentiate both sides of it with respect to x, and then we algebraically isolate to solve for dy dx. In this case, the derivative of 1 on the right is 0. On the left-hand side, if we work term by term, the derivative of x squared with respect to x is an explicit derivative, i.e. the variables agree. So that would just be 2x. But when that derivative hits y squared, now y is a different variable from x, and this is what we'd refer to as being an implicit derivative. And our rule of thumb is we differentiate that y squared exactly how we would like to y, and because it's an implicit derivative, we immediately multiply it by dy dx. And you can remember that rule of thumb, or you can note that it's really kind of just the chain rule in disguise. Thinking of y as a function of x, if it's squared, the chain rule tells us we differentiate that outside function, evaluate it at the inside function, and multiply it by the derivative of the inside function. So the derivative of y squared with respect to x should be 2y dy dx. And if you prefer, you can certainly replace that dy dx with a y prime. At this point, the calculus is done, and what we are left with is isolating that dy dx. So whatever terms involve dy dx, you leave them on the left or you move them to the left. And then you isolate them. So in this case, dy dx is equal to minus x over y. And this is what we've been asked to find in part A of the problem. Now remember, we still have the same graphical or geometric interpretation of the derivative we had previously. At a point on the curve, the derivative will give us the slope of the tangent line. So with this in mind, part B of the question asks us to find the equation of the tangent line at the point 0, 1. So let's just go ahead and note exactly what the form of that tangent line would be. It's y equals whatever the slope is, and remember the slope would be the derivative evaluated at that point 0, 1 times x minus 0 plus 1. And the only quantity we need to figure out in this case is the slope of that tangent line, which we can fairly quickly and easy just calculate to the side. So dy dx at 0, 1, we replace each x with a 0 and each y with a 1. So the slope of our tangent line in this case is 0. That is, we have y equals 0 times x minus 0 plus 1, which is really just y equals 1. And just to make sure this agrees with our intuition, if we go to our curve and look at the point 0, 1, when we draw the tangent line at this point, we see that it's going to be horizontal, just touching the circle at that point 1, 0. So yes, the equation of that tangent line really is y equals 1. And once again, let me just point out notationally, when you are evaluating dy dx at a point, we indicate that by drawing a vertical line and subscripting it with the point of interest. What I do not want you doing is writing dy dx equals and then just simply substituting it in. That would be an abuse of notation. And the last thing we'd like to do in this example is note, well, we've found the derivative. Could we also find the second derivative? So let's see about that. If we would like to find the second derivative, what we need to do is just remind ourselves what is a second derivative. And a second derivative is really nothing more than the derivative of the first derivative. And lucky for us, we know exactly what that first derivative is. That's what we calculated in part A of this example. So what I would like you to do at this point is to replace that dy dx with minus x over y, and then spend 2 or 3 minutes and see if you can come up with a formula representing the second derivative. And note it should only depend upon the variables x and y. Okay, so hopefully you've done that, and if not, you certainly should. There's still time to pause the video now and go through the computations. If I would like to differentiate minus x over y with respect to x, this is going to be a chain rule problem. And the chain rule tells us we take, what, low d high minus high d low, all divided by low squared, which leaves us with 2 derivatives to calculate. So just working our way from left to right, the derivative of minus x with respect to x, this is an explicit derivative. Those variables agree. And the derivative is minus 1. Then we are subtracting away minus a minus x to make that a positive x times the derivative of y with respect to x. So this is an implicit derivative. And in fact, we've already encountered this. The derivative of y with respect to x is, as expected, simply a dy dx. And then we note at this point, it's tempting to stop and say we've done all of our derivatives. What we have is a perfectly good formula for the second derivative. And that's kind of correct. There's just one more thing we need to do. This formula for the second derivative should only involve x's and y's. So we need to rewrite dy dx. But as noted, we've already done this to start the problem. This quantity is simply minus x over y. So if we put this all together, we have the second derivative is equal to minus y plus x times dy dx, which is minus x over y, all divided by y squared. And of course you could simplify this further, but this is a perfectly good formula representing the second derivative, and I'm going to leave it exactly as is. In our next video, we will explore a similar example where we are once again asked to find a derivative implicitly, but then do something a bit different with it. So stay tuned and take care.